Welcome in chemistry education. In this video, we will see the volumetric analysis. In volumetric analysis, the neutralization titration, complexometric titration, redox titration, precipitation titration, out of which in my last video, we already saw the neutralization titration. In this video, we will see the complexometric titration. Now, complexometric titration, the name itself giving the meaning for this titration. We know the titration is the reaction where we can measure the unknown concentration by formation of the complex. And after completion of the complex, the indicator shows the change in color. And from that, we can find out how much quantity is required to complete the complexation. Now, complexometric titration, here it is a form of volumetric analysis in which the formation of colored complex is used to indicate the end point of the titration. And complexometric titration are particularly used for determination of the mixture of the different metal ion solution. At every time we can see the concentration or measure the concentration of one of the metal ion at a different particular space or a specific pH. Now, for complexometric titration, we are using the complexing agent. It forms the complex, stable complex with the certain metal. Now, in which the complexing agent, there are a number of complexing agents are there, out of which the EDTA, that is ethylene diamine tetraacetate. Here, ethylene diamine tetraacetate. Now, this agent forms the octahedral complex with the metal ion. It's a stable complex, and which shows the change in color in the for the indicator. Now, this particularly the EDTA is stabilized by forming the disodium salt of ethylene diamine tetraacetate. Now, it interact with the metal ion. Now, it forms the octahedral geometry. Suppose this is a metal ion and it is connected with the 4 oxygen atoms from the acetate group, 2 ethylene, that is a nitrogen from the complex, and 2 ethylene groups are there, diamine groups are there, and it forms the 2 nitrogen and 4 oxygen. It forms the octahedral geometry with the metal ion. Now, this perfectly this geometry is based. It forms the stable complex into the central metal ion, and therefore it forms the coordinating bond, 4 coordinating bond with from the oxygen, 4 oxygen, and from 2 from the nitrogen. In this way, the stable geometry, octahedral geometry, forms with the help of one ligand, and therefore it is a monodentate ligand. It forms the stable octahedral geometry. Now, formation of the stable octahedral geometry, the central metal ion. Now, for example, in case of the transition metal ions, every metal ion gives the form the stable complex with the EDTA at a particular pH, and therefore this ligand or EDTA compound is used as a complexometric agent to form the stable complex. Now, for adjustment of the pH, now when we are thinking about this titration, the EDTA titrations are very sensitive for the pH. It requires the buffer solution for various pH. Starting from 2 pH to the 14 pH, we can prepare the buffer solution, and at a particular pH solution, the specific metal forms the stable complex with the EDTA, and therefore we can use this reagent for complexometric titration. The specific metal ion forms a stable complex at a different pH, starting from the acidic to basic pH. The formation of complex is controlled by pH, and this limit is a plus or minus 0.5 to plus or minus 1 pH. Within this range, we can find out form the stable complex. For adjustment of the pH of the buffer should be done with the help of pH meter. We can measure the pH of the buffer solution by using the pH meter. Now, for these type of titrations, we are using the some different indicators. Now, these indicators are, we have to prepare the 1% solution, maybe in the water or maybe in the alcohol. The color change of the indicator in a solution should be visible. Now, color starting from the visible color, we can observe that there is a change in color, because sometime what happened, the blue color and green color, when we are using the dilute solution, the blue to green color we are not observing properly. Similarly, yellow to orange color. Now, when dilute solutions are there, we are not observing, and therefore such a type of titrations, they are in the dilute solutions, and therefore we require such a type of indicator which shows the change in color or sharp change in color. The color of the solution should be specific for the particular metal ion. For one metal ion, it shows a different color than the other metal ion, and therefore the metal EDTA complex, this color must be more stable or sharper than the change in the metal indicator color, and the indicator must be sensitive to the metal ion. When we plot the graph for the different metal, as we adding the indicator and EDTA, then we observe that the nature of the graph is like this. When EDTA is adding from the solution and we are measuring the PM, that is a metal ion concentration, and when we plot that, the nature of the graph is like this. And here the Erichrome black tea indicator, this indicator is most important, and it gives the tremendous change in color for the number of metal ion at a particular different pH, and therefore ethylene Erichrome black tea indicator is used for most of the complexometric titrations. Now there are so many type of indicators are there. This is the structure of the Erichrome black tea indicator. This is the Mur oxide indicator. This is the fast sulfone black F indicator. This is a pattern and reader indicator. Now Erichrome black tea and pattern and reader indicator, they are mostly used. This indicator is mostly used for the alkali and alkaline earth metal, and this indicator shows the change in color shown for the most of the transition metals. Now in this way, there are so many type of indicators are there, but these indicators are generally used for the titrations in for the alkali metal, alkaline metal, as well as the transition metal ions. Now for this titration, we have to prepare the solution properly. Now for example, suppose the solution of the EDTA, we have to prepare the EDTA solution, exactly that 9.31 gram of EDTA, that is a EDTA salt of the sodium, so disodium EDTA dissolved into the 500 ml of the distilled water, and to get the this solution for the complexometric titration. Now we know the buffer solution. This buffer action, for the buffer action, it remains the constant pH. For this purpose, the most of the transition metal, it required the basic buffer. Now for example, here for 10.5 pH buffer, we have to dissolve the 7 gram of ammonium chloride and 57 ml of concentrated ammonia and dilute to 100 ml by the distilled water. This is the buffer solution for the 10.5 pH. Now so many buffers are there, for starting from the acidic pH like sodium acetate and acetic acid, then for 7 pH, neutral pH, then basic buffer. We can change the concentration by changing the amount of the solution. We can prepare the buffer for the different pH, and the pH of the buffer is measured maybe by the pH pen or pH meter. Then standard solutions for the suppose magnesium chloride, zinc chloride, these compounds, these solutions are used as a standard solutions for the titration of the EDTA, for standardization of EDTA. Now for magnesium chloride, it's a 2.45 gram of magnesium chloride hexahydrate. We have to dilute, dissolve into the and to form the 500 ml total solution by using the volumetric flask. Then Erichrome black tea indicator or any indicator, just we have to up to the 1% solution of the indicator we have to prepare either in the dissolve into the water first, then we have to see in the alcohol, then we have to see the basic buffer like ammonia, HCl, like that. In this way we have to prepare the proper solution of the indicator. Now there are three types of the complexometric titration. First is the direct titration, the second is the back titration, replacement titration. These type of titrations are the complexometric titration. Now in case of the direct titration, just metal we have to react with the indicator and directly this EDTA ligand, and directly we get the formation of the complex, and the indicator shows the change in color. There is a no remain the metal, and therefore from that direct titration we can use. Now in case of the back titration, whatever the ligand is added completely and it react with the specific metal ion, and remaining ligand can be identified with the help of another metal is added. For this metal, how much ligand is there, what is the amount of ligand is taken and what is remain. From that we can back titrate it, we can titrate the complexometric titration. In case of the replacement titration, there are three types of replacement titrations are there. Now one in first titration completely transfer the all ligands, and in another case one of the ligand get replaced by the another ligand, and from that we can see the change in color. From that we can identify the complexometric titration, how much concentration of the metal ion present in the solution by using the complexometric titration. Now first we see the direct titration. Now here the metal salt solution titrated with the complexing compound solution, and after adding the buffer solution suitable and suitable indicator, it directly titrated with the standard EDTA solution and to form from the burette, and we get this type of specific complex. These are the ligands and this is metal ion solution. When it interact with the metal ion solution, and then the ligands are interact with the metal ion solution, and metal forms the stable complex with this ligand, and to get the formation of stable compounds. And from that we can directly titrate. Indicator shows the change in color, and we can measure the direct titration. Now, for example, the direct titration, suppose we are taking the flask, and in that flask the metal ion solution is taken, and we are adding the indicator for as a bromo Erichrome black tea indicator or any another indicator we have to add into the flask. Now first is the related to the magnesium sulfate. Suppose for example an indicator we are added, the indicator shows the change in color. Suppose that magnesium formed the magenta color complex in the buffer solution, the basic buffer, and we observe that the magenta color that is a reddish color, wine red color formed with the help of metal ion with the indicator. And then when we are adding the EDTA solution from the burette, we observe that the next reaction, that's this magnesium indicator color, that is a wine red color solution, when titrated with the sodium EDTA, then we observed that after completion of the titration, we observed that the change in color in the indicator, that is from the wine red to the blue color, slightly changes color. When we are adding from the burette the EDTA solution, we observed that there is a change in color, that is wine red to blue color. And when blue color is appear completely, then the completion of the whatever the magnesium present in the solution or metal solution present in the solution, it completely interact with the EDTA the compound, and we get the magnesium EDTA complex, and indicator shows its own color, that is a blue color. Now in this way this direct titration can be done. Now in case of the magnesium in the, when 25 ml of magnesium sulfate solution is added, then for 5 ml of buffer solution is added, 3 drops of Erichrome black tea indicator is added, it gives the wine red color, and when we are titrating it gives the blue color. Now when 1 ml of EDTA solution is added, disodium EDTA solution is there, then 2.432 milligram of magnesium must be there. And now this type of titration can be useful for the magnesium, manganese, zinc, cadmium, mercury, copper, aluminum, iron, cobalt, nickel, platinum, etc. Now every metal ion gives the change in color or specific complex at a particular pH, and therefore we can find out the unknown concentration of the metal ion which is taken into the flask, and from that this relation. Suppose we require the 1 ml of EDTA solution, it must contain the 2.43 milligram of the magnesium. In this way, every metal ion can be identified with the help of this EDTA titration. Therefore, it is called as a direct titration. Okay, now in case of the back titration, we observed that the whatever the ligand solution is there, this ligand solution is completely allowed to react with the metal ion solution, and whatever the amount of ligand remain into the solution, it can be find out easily with the help of the another metal. For example, this is the one metal, and these are the ligands are there, they form the complex, and remaining ligands are there. This remaining ligand form the complex with the another metal, and remaining ligand concentration can be measured. Now in the back titration, what happened, the excess of the standard solution of the EDTA is added first into the solution, and to the solution containing the analyte. Whatever the metal ion solution is there, it forms the complex first, and when the reaction is completed, the excess EDTA is back titrated with the end point using the magnesium or zinc metal ion standard solution with the help of indicator of the electron black indicator. And when it interact with this the metal ion solution, the initially the ligand is there, therefore it shows the electron black indicator shows the blue color, and when we are adding the metal ion solution to react the excess EDTA, we get the formation of the change in color, that is the blue to wine red color. And due to at this end point, we are seeing that how much ligand is remain, how much we are added initially, we know that how much remain is there, that remain can be find out, and therefore whatever the initially it was consumed, it can be calculated, therefore it is called as a back titration. Now for preparation of the sample solution, now generally what happened, the sample preparation already in the solution, then such as a fresh water, sea water or a milk, no further preparation is needed, because these are the already in the solution form. But for solid sample, what happened, like such as egg shells, limestone, whatever the compounds are there, solid compounds are there, for this purpose we have to use the procedure like accurately weigh about 0.5 gram of the solid into the small beaker or conical flask, then we have to add the 20 ml of dilute hydrochloric acid to react with this to give the formation of preparation of the dissolved salt. And then this after completion of the dissolution, then neutralize unreacted acid with the dilute sodium hydroxide, and then the solution until the pH of the solution is nearly equal to the 7. We have to stop the titration, and this solution is used as the for the solution for as an analyte. Now for such a type of eggshell, the inner membrane of the will be remain undissolved part. It can be carefully removed from the solution, and this solution transferred to dilute particular like 100 ml or 500 ml, 250 ml like that, and from that we can take the small quantity. Now for example, suppose EDTA solution for the preparation of the standard EDTA solution, we have to pipette out 10 ml of EDTA solution with the conical flask, then we have to add the 10 ml of ammonia buffer solution, and then we have to add the 1 ml of erythrom black tea indicator. Now this solution get titrate with this EDTA solution with the standard magnesium chloride solution or zinc chloride solution until the end point reaches to the color changes from the blue to pink color or wine red color. Now it having the determination of average titer of the magnesium chloride solution and determine the number of moles given for magnesium 2 plus is to EDTA is a 1:1, and then from that 1:1 complex we can calculate the concentration of the EDTA solution. In this way we can standardize the EDTA solution, and then for sample solution, like pipette out 10 ml of sample solution into the conical flask, we have to add the 20 ml of 0.05 molar ligand 1, that is the EDTA solution, and then 10 ml of the ammonia buffer solution and 50 ml of distilled water, then and we have to add the indicator and directly titrate with the standard 0.025 molar moles per liter magnesium chloride solution, and we get the colorless blue color to pink color. Now in this way we can use this titration for the seawater, and for the titration for the method for fresh or tap water, from the tap water, similar procedure we can use. Just like add 100 ml of sample solution into 250 ml conical flask, then prepare the 0.005 molar EDTA solution moles per liter EDTA solution by diluting it to get the 1:10 ratio. Then we have to add the 20 ml of the diluted EDTA solution and 10 ml of ammonia buffer, 1 ml of indicator, and we have to titrate with this solution, and the color changes from pink color appear, or blue to wine red color. Now, for the calculation, we should concentrate on the concentration, how calculations, because whatever the amount quantity get diluted, we have to think over that, and we have to calculate for calcium, magnesium determination simultaneously can be calculated in terms of the calcium carbonate. What is the amount of calcium and magnesium, and from the solution we can analyze with the help of this. Now, for example, the another example like the hardness of water. Now, for measurement of the hardness of water, we have to use this method as a standardization of EDTA. First, we have to standardize the EDTA with the help of zinc sulfate solution, as we know the procedure, and then estimation of the total hardness. Like just like a 25 ml of hard water plus 5 ml of buffer solution, we have to add here. Then the 2-3 drops of the indicator we have to add, and EDTA solution from the burette we have to add. The color change is a wine red to the blue color. After a certain time, we observe that this wine red color changes to the blue color. This is the end point of the titration, and from this whatever the result reading of the on the burette, that reading, that is considering the XML or YML, and we have to substitute here, and from that we can calculate the hardness in terms of the calcium carbonate. In this way, this complexometric titration can be used for the measurement of the hardness of the water. Now, in this way, we use this. Now, in case of the replacement titration, now sometime what happened, the one of the ligand get completely replaced by the other ligand, and therefore one metal forms the complex with the first ligand. It completely replaced by the another ligand. Now, how much ligand get removed from the complex? From that also we can find out the what is the concentration of ion, metal ion, or how much ligand required to form the complex. From that also we can find out the ligand. It depends on what type of ligand. Now, suppose these two type of ligands are there. From the green type of ligand, we can find out how much it is removed, and from the orange type of ligand, how much it is consumed. From both, we can find out the replacement titration. That is a complexometric titration, when one can find out the metal ion concentration. Another method is where one of the ligand get replaced by the another ligand. Now, from this complex, this ligand is replaced by this ligand, and how much ligand get consumed. Now, on the basis, the how many type of molecules or complexes are there in the complex, that can be find out. This is the variety of the complexes are there. Total complete replacement of the ligand, as well as one of the ligand from the complex can be replaced. In this way, we can use the complexometric titrations.